Welcome to Le Chatelier's principle. We know that given a reaction equilibrium, like this one, that a couple things are true. First of all, we know that the rate of the forward reaction equals the rate of the reverse reaction. And we also know that at equilibrium, the concentrations of reactant and product have reached a balance. In other words, their concentrations are constant. Now it turns out this state of balance can be modified if the conditions change, and this is known as Le Chatelier's principle. Le Chatelier's principle says that if a stress is applied to a system at equilibrium, the equilibrium shifts to relieve that stress. So we're going to get to what this idea of shifting means in a second, but first let's look at what a stress is. And a stress is a change in any condition that affects the rate of reaction. So we know what a couple of these stresses are already because we've talked about things that affect reaction rate. So things like temperature changes, changes in concentration, and also pressure changes. But pressure changes are for gases only. So only equilibria involving gases will be affected by pressure. So we're going to see what happens to an equilibrium when these stresses are applied to the system. And it says in the principle that it's going to shift. So as we look at some examples, we'll see what this shifting really means. First, let's look at the effect of changing concentration. We already know that the reaction rate depends on molecules colliding. So if I increase the number of molecules in an area, I'm going to increase the rate of collision and increase that rate of reaction. And because equilibrium is based off the forward and reverse reaction rates being the same, if I change the amount of reactant or product, I'm going to affect those reaction rates and they may not be equal anymore. So let's look at an example of changing concentration. First, I'm going to add a reactant. And let's just choose N2 gas, nitrogen gas. Because I've added more reactant, I'm going to increase the rate of the forward reaction. And because the forward reaction rate is increased, we say the equilibrium shifts to the right. And the result of that is that more products are formed. And this should make sense, because the system is trying to get back to a balanced state. And if I add a reactant, nitrogen gas, it's going to counteract that by shifting to the right and making more products to restore equilibrium concentrations of product and reactant. As another example, I could remove a reactant. Let's remove some hydrogen gas. Having less reactants is going to slow down the forward rate. And if I slow down the forward rate, that means the reverse rates are now suddenly larger. And we're going to have an equilibrium shift to the left. And with the overall equilibrium shifting to the left, that means I'm going to use up some of this NH3, but I'm going to produce more nitrogen gas and produce more hydrogen gas. So that's an interesting consequence of removing something from the reaction, is that the equilibrium tries to restore the balance by creating more of it again. Now there's a quick method you can use to figure out which way the equilibrium is going to shift based on a given change. So to show that, we're going to see what happens when we add some product, NH3. So when I add some product, I'm adding this one over here. So this is getting larger. If that side gets larger, that means the reactant side is less than the product side. Now remember, this is just a trick to remembering the shift. The actual amounts may not be greater or less than. But the fact that I'm adding something to the product side, I'm saying that lets me put a reactants are less than product statement in here. So now that I've put in this less than sign, I'm going to make it into an arrow. So this tells me it's a shift to the left. And you can see this method is going to work with even one of the earlier examples we talked about. Let's revisit this adding N2 scenario. If I add N2, that's going to increase this reactant, so I'm putting it under this N2, means the reactant side is going to be greater than the product side, and the shift is to the right. So this system of drawing arrows is just one way of figuring out which way the shift is occur, but it's a convenient method and it works pretty well.